The challenge for the communications sub-team was to design a wireless link that could send data through human tissue at a rate of 4,024 bits per second using a minimal amount of power. Research told us that existing wireless technologies such as Bluetooth or Zigbee, although they may have low power consumption in comparison to others, still provide at higher data rates over a larger distance than we required for this project. Research also told us that the lower the frequency, the less the attenuation that would be caused by human tissue. If we designed our own bespoke communications link, we could reduce the distance and data rate, which would hopefully provide a power saving, and could also choose a lower frequency to reduce the degradation of the signal and hopefully improve the bit error rate. To design this bespoke link, we had to choose both a frequency to operate at and a modulation scheme to modulate the data to the desired frequency. As we had two team members working on this part of the project, we decided to split the tasks. One person would look at the frequency selection and the other would look at the modulation scheme design. As these two tasks were to be completed in parallel, we decided the software-defined radio would provide the flexibility that we required to experiment with different modulation schemes, allowing the frequency to be decided at a later date. Initial investigations were carried out in National Instruments LabVIEW software with the Modulation Toolkit add-on, allowing graphs to be plotted showing the bit error rate and capacity against the signal-to-noise ratio for 11 different schemes. Following this, the NI Universal Software radio peripherals enabled us to define radios, again using LabVIEW software. When the frequency was decided, we could simply plug in the appropriate antennas and set the frequency in the code.
To find the best operating frequency for the through-body communication link, we tested the signal attenuation through a human tissue simulant at different ISM band frequencies, including 2.4 GHz, 868 MHz, and 433 MHz. For the measurement, we used the Anritsu MS-2036A vector network analyzer and placed monopole antennas in an anechoic chamber with pork meat in between to simulate the human tissue. Measuring the S/1 parameter, which is the ratio of power received by antenna 2 and the power transmitted by antenna 1, we could determine that the attenuation is the lowest at low frequencies. Based on this test result, we decided to use 433 MHz as the operating frequency for the through-body communication link in this project.
A further use of the ESRPs was to test the final system. They were set up to act as controlled interferers with the same modulation schemes as some 433 MHz modems. This allowed us to see how our final system coped with interference from other radio sources, which would be extremely important as the patient may not receive the treatment they require in some medical use cases if communication between the base station and the capsule was lost.
To provide communication capabilities in the scaled capsule, it was necessary to develop an embedded wireless communication system. The most important component was the transceiver chip, which had to be very low power for our application. The best suitable transceiver was found to be the CC1101 from Texas Instruments. It is a low-power wireless transceiver that can operate at 433 MHz and offers the flexibility to configure modulation scheme and output power in software. A prototype PCB was designed in the Altium design tool with the CC1101 transceiver, a Yago chip antenna, and the microchip microcontroller which connects to the CC1101 over an SPI interface. The performance of that prototype PCB was tested in combination with the Texas Instruments Smart RF Studio software and their evaluation board acting as receiver. Measurements with the prototype PCB have shown that the communication link works reliably through porcine tissue at a distance below 2 meters, which covers the scenario of having the capsule inside the body and the base station body-worn. For the lowest output power level of -30 dBm, the power consumption for the wireless transceiver chip is approximately 40 milliwatts.